Hi everyone, welcome back to Synthesis Workshop. I'm your host Alicia, and today we're joined by Max Palkowitz for an introduction to electrochemistry. Max began his studies at Boston College, where he obtained his Bachelor's of Science in Chemistry in 2018. Here he performed research under the guidance of Professor James Morgan. He then moved to Scripps in 2018, where he joined the Baran lab for his doctoral studies. Here Max focused on electromediated radical cross-couplings, giving him the expertise to deliver us this wonderful lecture today. Max has since joined Bristol Myers Squibb, where he is currently a senior scientist. And with that, I'll hand it over to Max. Welcome, and thanks again for joining us.
Thank you for the kind introduction. So electrochemistry is a field of chemistry that I am deeply passionate about. I spent a good chunk of my time during my PhD learning it from essentially nothing, and I am proud to say that after all this time, I still feel like I don't know much about it. But I have learned a few things, and I am really excited to share that with you all today. So the focus of this course will be more centered on modern applications of this redox platform in organic synthesis. However, let's kick things off with some basic fundamentals. Okay, we all had to take physics in order to be chem majors in college, so let's take a trip back to that painful time in our lives and revisit something called Ohm's law. So Ohm's law states that the observed voltage in a circuit is directly proportional to its current and resistance through that circuit. Current is simply just a measure of the amount of electric charge passed per unit time, which we'll just call amps, and potential or voltage is a measure of the amount of work required to move that charge through an electric field or a piece of circuitry. So finally, a resistor is literally just anything that resists electrical flow and loses that energy to, say, heat, light, etc. This should be intuitive, right? If we apply a constant potential to this hypothetical circuit with a high resistance, then there will be little current that can flow through it, and vice versa. If we hold current constant and the resistance is super high, then we need a really high potential in order to push that charge through the circuit and vice versa. This is the exact same thing in electrochemistry. Instead of thinking about a resistor, we think about chemical reactions, and these reactions can require either a very high or very low potential depending on what we are trying to achieve. So what actually happens inside the flask when we run an electrochemical reaction? How do we escape college physics and return back to organic chemistry? In the flask, before we even apply potential, the reaction mixture is filled with various charge carriers. This could be your substrate, your electrolyte, or anything that is really charged or capable of becoming charged pretty easily. Right now, there is nothing driving any kind of charge separation and thus potential difference. Next, we flip the switch and electrons are rushed from the anode and pushed into the cathode as represented by these yellow dots. This creates both an oxidizing anodic environment as well as a reducing cathodic environment. This applied potential difference causes a movement of charge in the flask where negative charge carriers are rushed to the anode surface and positive ones to the cathode surface. Our substrates are also in this mix too. This process in combination with electron flow is our current. Now that we have a current and a voltage, we can begin thinking about substrate oxidation and reduction. One key thing to remember is that electrons do not pass through the solution. It is the substrates that provide the electrons for both electrode events. This is critical for there to be a complete circuit. If a substrate is oxidized, then something must be reduced in an equal amount. Electrochemistry requires balance of redox events at each electrode or current simply will not flow. For instance, in the Shono oxidation, which we will discuss later, amine oxidation at the anode is paired with proton reduction at the cathode. Both events are required for the reaction to work. Finally, chemists like stoichiometry, so throughout the literature and the rest of the talk, we'll simply refer to the equivalence of electrons as a farad or a Faraday per mole. For example, if a reaction requires one equivalent of electrons, then it's written as 1 Faraday per mole. If it needs 2, then it's written as 2 Faraday per mole. Rarely are electrochemical reactions perfectly efficient, so you'll often see Faraday per mole that exceed the amount in theory needed, and that's totally fine. Charge can be lost through many means, such as solvent oxidation or reduction, charge organization, or side product formation. Shannon Stahl and Mohammed Rafi have a really wonderful electroorganic chemistry short course that dive really deep into many of these variables, and I highly recommend folks go there for a real probe into these concepts. Fortunately, much like NMR, we don't really need to understand every nuance to be able to design, run, and discover our own electrochemical transformations. All we need is the equipment, so let's take a look there. An electrochemical cell consists of a few simple parts. First, you need a power source that can control the current, often referred to as a galvanostat, and the potential, referred to as potentiostat. Modern electrochemical devices can do both, thankfully. Next, you obviously need electrodes, and this is where the real flavor of electrochemistry comes out. Since electron transfer occurs directly at the solid interface, the choice of electrode material can drastically alter the outcome of the reaction. I put a few common choices here, but there really are countless options for electrode material. You have ones that are porous and thus have a high surface area, such as nickel foam and reticulated vitreous carbon, or RVC for short. These are great for getting good exposure of substrate to the electroactive surface, as well as having a mild, low current density, although they may be more challenging to scale. Next, you have ones with very low surface area, like graphite or platinum, and finally you have electrodes that act as redox auxiliaries themselves, such as zinc or magnesium. These electrodes themselves can be oxidized sacrificially and are great choices for net reductive transformations, often called sacrificial anodes. The reaction of interest takes place at the working electrode and is paired with a counter electrode. If you're running a constant potential electrochemical experiment, then a reference electrode is needed. Running one of these experiments without one would be like heating a stir plate without a thermometer. So this third electrode has a well-defined redox couple that potential at the working electrode can be measured against, much like you have a thermometer measuring temperature in a hot plate. Next, most reactions need solvent, and electrochemistry is no exception. However, the choice of solvent is admittedly more limited than most organic reactions, just because they involve charge carriers and chemical redox. As such, the solvent must not only fully dissolve the reagents, but the electrolytes too, and also be stable under the reaction conditions. Typically, polar aprotic solvents are used, such as DMF, DMA, acetonitrile, etc., and solvents with high dielectric constants are preferred, since they will naturally have a lower resistance to current, but there are some examples where solvents like THF and DCM can be used. We will talk about these later in a few case studies. Finally, an electrolyte is needed. This additive generally improves conductivity and can even overcome a poor solvent choice. Electrolytes can be any salt so long as it is stable under the reaction conditions. Commonly, tetraalkyl ammonium salts or perfluoroborate salts are picked due to their inert properties. Sometimes metal catalysts can even serve as electrolytes. It may not seem like there is an electrolyte always added to an electrochemical reaction intentionally, but something in there is aiding in charge transfer and organization, and it's thus acting like an electrolyte. It's just a matter of figuring out what it is. I think it's important to address the fact that yes, there are lots of moving parts to electrochemistry, both in the fundamental theories as well as just running the reactions at the bench. So why even put up with it? Why is it worth even considering as a tactic? For starters, electrochemistry can confer a degree of selectivity that is unmatched by chemical reagents. Chemical oxidants and reductants operate at fixed potentials or fixed potential windows. Electrochemistry can engage functional groups at many different potentials and also avoid deleterious side reactions caused by chemical reagents. A great example of this can be seen in Pat Harran's synthesis of diazonamide analogs. In their initial approach, this key macrocyclization was carried out using a hypervalent iodine reagent PETA. While it afforded the desired product, the yield was low and the profile was riddled with byproducts. Mechanistically, these arose from side reactivity of the activated phenol and the neighboring amide oxygen atom, resulting in an undesired spirocyclic byproduct. This competed with the desired phenonium capture at the ortho position by C3 of the linked indole to forge the key macrocycle. Recognizing the utility of electrochemistry to engage in chemoselective redox, the Harran group turned to this platform to forge the macrocycle. Taking the same substrate under oxidative electrochemical conditions led to formation of the radical cation of the pendant indole, which can be rationalized by its relative electron richness compared to the phenol. Next, the oxygen atom can attack C2 of the indole cation to forge the first key bond and also quenching the cation nature of the intermediate. Next, the phenol can act as a radical acceptor for the indole radical, resulting in formation of the key carbon-carbon bond of the macrocycle. Finally, anodic oxidation and loss of a proton can afford the desired product selectively. By engaging in direct electron transfer over chemical activation, the byproduct profile was significantly cleaner and allowed access to this key intermediate in synthetically useful amounts. In addition to selectivity, electrochemistry can also be used to provide safer alternatives to reactions that require reactive intermediates or dangerous reagents. For example, Perichon and coworkers demonstrated how cathodic reduction of alkyl chlorides can be used to safely perform Barbier additions to ketones and aldehydes without the need for preparing discrete organometallic reagents. Here, electrolysis can be used to achieve mimicry of pyrophoric reagents. Finally, electrochemistry also has the potential to be highly scalable. The anodic oxidation of terpentyltoluene to its dimethyl acetal and concomitant ester reduction to forge the corresponding lactone is carried out by BASF on 400 gram scale routinely. While electrochemistry is in principle scalable, I think the field still has a bit of ways to go in translating robust small-scale bench chemistry to higher-order process settings. There, the issues are not so much chemistry, but rather engineering in nature, which is one of the most unfortunate downsides of the tactic. Okay, now that we have covered some of the basics, I figured this would be a good opportunity to dive deep into how the community has been using electrochemistry and what some of the common transformations are in that toolbox. Perhaps one of the most well-studied electrochemical transformations is the Shono oxidation. This is a reaction that takes amines, usually with an electron withdrawing group attached, and generates the corresponding aminal and protic solvent. Mechanistically, this operates via a two-electron oxidation of the tertiary amine to form a reactive iminium cation, which simply gets quenched by the conjugate base of the solvent used. The reaction is balanced by proton reduction at the cathode. Rather than go through every single use case of this reaction in the lit, I wanted to just highlight a few recent examples. First, the Lin group demonstrated a neat take on this reaction where they used the Shono oxidation to form trifluoroethanol adducts under standard Shono conditions. Using these adducts, they were able to diversify them with a wide range of carbon-based nucleophiles such as organozincs. This resulted in a neat approach for a formal CH methylation which tolerated complex pharmaceutical molecules such as this TPRA1 antagonist. The only limitation of this approach, and more generally the Shono, is the need for an electron withdrawing group on the nitrogen to temper the reactivity of the iminium. The Shono oxidation has also found utility in natural product synthesis as well. Here, the TAN group elegantly accessed the key oxidation pattern and caged architecture of the asfidofractanine natural products. Shono oxidation of the cyclic allylamine resulted in gamma etherification, followed by intramolecular capture of the resulting iminium cation in a single reaction sequence. So what happens when you have multiple sites of reactivity for a Shono? If you can't control it with sterics, then varying the identity of the electron withdrawing group can alter the outcome by stabilizing one iminium over another. Here, the N-cyano favors a more substituted iminium. One can also consider installing a functional group to direct oxidation, then remove it after the reaction is complete. Here, these so-called electro-auxiliaries can be oxidized to a leaving group to promote iminium formation at the point of attachment. Another important named reaction in oxidative electrochemistry is the Kolbe reaction. In fact, this reaction was actually discovered by Michael Faraday when he electrolyzed acetic acid in observed gas evolution. It wasn't until later that the process and the products were fully understood by Kolbe and others. The classical Kolbe reaction involves the anodic one-electron oxidation of a carboxylate. This rapidly decomposes by liberating CO2 and generating an alkyl radical. This radical then rapidly dimerizes to afford a new carbon-carbon bond. This decarboxylative dimerization is a surprisingly useful tool in synthesis. In fact, E.J. Corey and his lab leveraged this tactic in the synthesis of onoceradiones alpha and beta, thus representing one of the early examples of electrochemistry in total synthesis. Dimerization is not the only terminating event that can be leveraged here. Becking and coworkers demonstrated that radical clocks could be intercepted with the Kolbe reaction. For instance, using a large excess of acetic acid, a methyl radical trap can trap the 5-exo cyclization product of an acid-bearing allylamine. Here, a large excess of acetic acid is needed, though, to favor heterocoupling. This reaction has also found utility in larger process scales, too. Quartenmont and coworkers developed a Kolbe annulation to make a key lactam intermediate recently. This reaction scale-up was dependent on thoughtful implementation of flow electrochemistry. If you want to hear more about flow chemistry, I would encourage you all to check out my best friend Gabriele's wonderful lecture on the fundamentals of flow chemistry in this same series. One of the biggest limitations of the Kolbe is the inability to perform these reactions in the presence of sensitive functional groups, owing to the high potential needed to carry out the reaction. The Baran lab discovered that by simply changing the waveform of the applied current, you can ameliorate these issues. This could be seen most evidently with the attempted Kolbe on the carboxylic acid bearing an easily oxidizable benzylic position. Under standard Kolbe conditions, only benzylic oxidation products were observed. However, switching the waveform to alternating current flipped the outcome, and the desired dimer was observed instead. So what's going on here? Well, most electrochemical reactions are run using direct current. In the Kolbe, this results in a high overpotential since the oxidative environment of the electrode is acidic due to water and solvent oxidation. Therefore, there is not much free carboxylate to undergo the oxidation. If the waveform is run under alternating current instead, then there is not sufficient time to build up a local pH difference, and carboxylate oxidation can occur at a much lower potential. This new waveform approach, dubbed rapid alternating polarity, or RAP for short, overcame critical limitations in the scope of the classical Kolbe reaction. Not only could the reaction now be performed more easily on scale, but a wider range of functional groups could be tolerated, as evidenced by the synthesis of this trifluoromethyl containing unnatural amino acid. However, again, a large excess of one of the acids is needed to favor heterocoupling products. Similar to the Kolbe reaction, the Hofer-Moest reaction is another useful electrochemical transformation that leverages carboxylate oxidation to do subsequent chemistry. Instead of stopping at the corresponding alkyl radical, this species is further oxidized to the carbocation, which is then trapped by some pronucleophiles. Classically, this is just water or alcohols in solvent quantities. Just like the Kolbe, the oxidative reaction is balanced by proton reduction at the cathode. The reaction has not been too popular in synthetic literature, but recent advances have made it more attractive for modern organic synthesis. Recently, the Baran lab demonstrated that the Hofer-Moest reaction can be used to forge hindered dialkyl ethers using a slight excess of the trapping alcohol. This reaction was not limited to just alcohols as nucleophiles. Water, carboxylates, and even fluoride could trap this electrochemically generated carbocation. In separate follow-up work, this platform was extended to azole alkylation as well, with minor changes in the reaction conditions. These electrochemically generated carbocations can be leveraged for olefin synthesis as well. In the absence of a reasonably potent nucleophile, these cations can easily eliminate to the corresponding olefin. However, regiochemical control is not perfect. Finally, the Lamb group recently showed how ureas and carbonates can be forged using a Hofer-Moest approach via an intermediate isocyanate. In all, the Hofer-Moest is a useful electrochemical approach to leverage the reactivity of high-energy carbocations under mild electrochemical conditions. Outside of named reactions, there are many examples in the lit of how electrochemistry can be used to facilitate redox processes that would be challenging to pull off otherwise. Perhaps one of the more well-known examples is the Baran synthesis of deoxymycin B. This carbazole dimer was only able to be forged via constant potential electrolysis. All other attempts with chemical oxidants failed to realize this key dimerization step in the synthesis. The Mulder lab has had a long and rich history of leveraging electrochemistry for complex molecule synthesis. In this vein, electrochemistry was leveraged to bring about Umplong reactivity of silyl-enol ethers. In the total synthesis of oleochol A, the Mulder lab carried out a cyclization strategy that involved electrochemical oxidation of a silyl-enol ether to forge the corresponding radical cation. This radical cation can be easily trapped by the pendant electron-rich furan to forge a central six-membered ring. Subsequent one-electron oxidation and loss of silyl cation gave the furan-fused carbocycle an 88% yield. Follow-up steps led to the completion of oleochol A using electrochemistry as the key enabling tactic. This enol oxidation tactic was recently leveraged by the Baran lab to achieve desaturization of enols to forge enones. Mechanistically, this proceeds via one-electron oxidation of the enol to the radical cation, which acidifies the beta proton enough, making it prone to base-mediated elimination. Once the olefin is formed, a second one-electron oxidation and loss of TMS cation restores the ketone. Anesols are also a reasonably electroactive functional group. Recently, my friend Brendan leveraged an electrooxidative cyclization approach in his synthesis of dragosins A through C. Electrochemical oxidation of this pendant anisole led to formation of a transient quinomethide that was trapped intramolecularly by the neighboring alcohol. Subsequent deprotection afforded dragosin A. This reaction was easily scalable on benchtop reactors to drive analog work of this natural product series. It is important to note here that all attempts to carry out this transformation using chemical reagents had failed. Electrochemistry was uniquely effective in facilitating this key macrocyclization. Collectively, these examples demonstrate how oxidative electrochemistry can be a useful tool to leverage native functionality to build up complex molecules rather quickly. Now that we have looked at many examples of oxidative electrochemistry, let's switch gears to reductive tactics. There are not really as many named approaches here, but there are a lot of overlap between the reaction conditions. Generally, the challenge of reductive chemistry is simply dialing in the deeply reducing potentials you need, and also ensuring that you don't oxidize whatever it is you just reduced. For the latter, this is typically solved by leveraging a divided cell or by using a sacrificial anode. These are special electrodes that undergo oxidation themselves and dissolve in the reaction mixture. They are usually metals such as aluminum, magnesium, or zinc that are easily oxidized. If you don't want to use a sacrificial anode due to the metal salts they produce throughout the reaction, then you can use an organic sacrificial oxidant such as a tertiary amine to balance substrate reduction. This is a bit harder to pull off in practice since substrate reoxidation is more feasible when sacrificial anodes are not used. As for solvents, amide solvents like DMF, DMA, and polar aprotic solvents like acetonitrile are most common. Obviously, product solvents are usually avoided since proton reduction would compete with substrate reduction. Halogenated solvents are also not ideal since they can be reduced to the corresponding anions rather easily. Speaking of halide reduction, reductive electrochemistry is well suited for functionalization of alkyl halides. The Lin group recently showed how tertiary alkyl halide reduction can be carried out electrochemically to generate carbanions that can be readily alkylated by primary electrophiles. Here, the tertiary or secondary halide is favored for reduction due to the stability of the resultant radical and subsequent anion that is formed. While the reaction tolerates a range of functional groups, a neighboring stabilizing group is needed on the tertiary halide. This reaction demonstrates a unique pyrophoric-free approach to carbanion chemistry. In the theme with the removal of pyrophorics from common reactions, the Baran lab demonstrated that electroreduction could also be used to achieve mimicry of lithium-ion reductions. In the presence of lithium bromide electrolyte, dimethylurea as a proton source, and TPPA as a cathode anti-fouling additive, arenes can be converted to their Birch reduction products without the need for metallic lithium using constant current electrolysis. These Birch-type reductions were also shown to be more functional group tolerant than the classical Birch conditions, as evidenced by many comparisons to state-of-the-art for this reduction. Arenes are not the only things that these deeply reducing electrochemical conditions could target. Epoxide opening, McMurray coupling, and ketone deoxygenation could be achieved using these Birch conditions. This reaction was also applied to the synthesis of suminerol, where previously Pfizer carried out a chemical Birch that required 2,500 liters of ammonia and over 6 kilograms of lithium to carry out. The key transformation they were trying to achieve was a tandem aziridine opening and debenzylation. Instead, the electrochemical conditions developed here were able to achieve the same tandem reduction without the hazardous conditions. Electrochemistry is great for accessing reduced forms of a variety of functional groups. An excellent use of reductive electrochemistry can be seen in the ketone-olefin coupling disclosed by the Baran lab. Here, ketones can be cathodically reduced to their corresponding ketyl radicals, which can then add unactivated olefins to afford tertiary alcohol products. Mechanistically, this proceeds via first a coordination of the ketone to the surface of the tin cathode. This was postulated based on the pre-peak current observed in the cyclic voltammogram of this substrate under the reaction conditions. The ketyl radical then adds to an olefin, generating a new carbon-centered radical. This radical is subsequently reduced to the anion and protonated to afford the desired product after workup. This reaction tolerated a range of functional groups and can be used to make a variety of tertiary alcohol products from easily accessible ketones without the need for hard nucleophiles. Okada esters have become a popular radical precursor in synthesis. These N-hydroxyphthalate esters are activated via a one-electron reduction, which after fragmentation and release of CO2 generates the corresponding carbon-centered radicals. These radicals can then be trapped by a variety of radical acceptors. The Baran lab leveraged electrochemical reduction of this functional group to realize an electrochemical decarboxylative borylation. Solvent had a dramatic effect on this reaction. If run purely in DCM, the reaction did not provide any desired product. However, if a small amount of DMF was added, then there is enough polarity to establish a potential difference, but more importantly, the DMF and B2-Cat2 pair can undergo anodic oxidation to balance the redox in the cell without the need for a sacrificial anode. This tactic was leveraged in the formal synthesis of josmicin, where this tetrachloro NHPI ester was converted to its corresponding boronic ester with inversion of stereochemistry due to the sterics of the neighboring methyl ester during radical capture. This boronic ester was then taken forward in an oxidative Suzuki coupling to afford the dimeric bis-cyclopropyl containing product. This electrochemical borylation, followed by palladium-mediated dimerization, was repeated once again to afford the tetrameric cyclopropyl containing fragment, which was taken forward to include the formal synthesis of josmicin. The modularity of this approach was enabled by electrochemistry's ability to undergo chemoselective redox of a readily accessible functional group in the form of a carboxylic acid. Okay, now let's quickly change gears. So we've talked a lot about how electrochemistry can be used to achieve oxidation or reduction of a substrate, so long as there is a counter reaction to balance at the opposing electrode. Most times, this reaction does not necessarily contribute to forging key bonds in the overall transformation. For instance, we have seen how oxidation is often balanced by proton reduction, and how reduction is often balanced by a sacrificial anode or sacrificial oxidation. That being said, there are a few examples of reactions where both oxidation and reduction contribute to the desired reaction. We refer to such reactions as operating under paired electrolysis, and there are a few flavors to this strategy which I'll briefly cover. First, there is parallel paired electrolysis, where two different starting materials both undergo electrode redox to generate a reduced and an oxidized product. The BASF phthalimide reduction and toluene oxidation is a great example of this, as both electrodes are used to create two value-added products which can be separated. Next, there is sequential paired electrolysis, where a starting material is oxidized to an intermediate which is then reduced to afford a product, and vice versa. A great example of this is the electrochemical conversion of oximes to nitriles. This proceeds first via anodic oxidation of the oxime to the nitrile oxide, and then subsequent reduction of that species to the desired nitrile. Overall, the process is redox neutral, as the product and the starting material are all in the same oxidation state, but proceeds via a paired oxidation and then subsequent reduction. Finally, the least common but no less important form is convergent paired electrolysis. In this mode of electrochemistry, two starting materials are both converted to two different intermediates, one via reduction and one via oxidation. These two intermediates react to form a single product. For example, the electrochemical Diels-Alder shown below generates both diene and the dienophile in a convergent paired electrolysis. First, hydroquinone is oxidized to benzoquinone at the anode. Meanwhile, this dibromxylene is reduced to the corresponding reactive diene at the cathode. These two electrogenerated species then react to forge the desired product. These redox platforms are attractive for designing new electrochemical reactions, but are slightly more challenging to realize, given the fact that you are now essentially optimizing two different electrochemical reactions that need to both be kinetically and thermodynamically feasible in order to effectively complete the circuit. So far, we have talked about transformations that involve the direct redox process at the electrode surface. Unfortunately, this tactic cannot be applied to all redox transformations in a general fashion. For example, some transformations such as CH oxidation are quite challenging. Even if we pull it off in a direct electrolysis fashion, the potential needed will be quite high and beyond the solvent window. This consequently would limit the generality of such a reaction. Instead, we can embrace an indirect approach by way of a mediator. A mediator is a redox-active electrocatalyst that can undergo a well-defined redox event and, in its reduced or oxidized form, can react with the starting material. In a sense, these mediators help transform electrochemical potential energy into chemical energy for a wide range of transformations. In this vein, there are a few different types of mediators. Tertiary amines such as quinculdine, when oxidized, are potent H-atom abstracting reagents. As such, there are many quinculdine derivatives that have demonstrated promise as HAT reagents in electrochemical CH functionalization chemistry. For example, the Baran lab leveraged quinculdine as a mediator for the electrochemical CH oxidation of unactivated CH bonds. Mechanistically, this proceeded first by anodic oxidation of the quinculdine mediator to its corresponding radical cation. This species is then set to abstract a hydrogen atom from the substrate, generating a new carbon-centered radical and a protonated quinculdinium cation. This radical simply gets captured by oxygen to generate the desired product, and the mediator gets regenerated via proton reduction at the cathode. Next, mediators such as ferrocene and triarylamines, when oxidized, become potent one-electron oxidants and can help facilitate a variety of otherwise challenging SCT processes. For example, the Zhu group showed how ferrocene-ferrocenium redox couple could be used to chemoselectively generate nitrogen-centered radicals that can undergo 5-exocyclizations with the pendant olefin to form lactams and carbonates. Mechanistically, this proceeds via first oxidation of ferrocene to ferrocenium at the anode. The iron 3 species here is a potent single-electron oxidant and can readily oxidize the conjugate base of the amide to form a nitrogen-centered radical. This also regenerates the iron 2 ferrocene species. The radical is then set to undergo a 5-exotrig cyclization to form the lactam. The resultant radical is then quenched with the stoichiometric amount of 1,4-cyclohexadiene to give the product. Finally, aminoxyl radicals such as TEMPO, when oxidized, become potent hydride abstracting oxidants and can interact with a wide range of functional groups. For instance, the Onomura group showed how a TEMPO derivative can be electrochemically oxidized to form a potent hydride abstracting reagent for alcohol oxidation. Mechanistically, This proceeds via first oxidation of the aminoxyl radical or hydroxylamine to the corresponding N-oxoammonium cation, which can facilitate the desired alcohol oxidation, thus regenerating the reduced form of the mediator. Interestingly, this redox was shown to be doubly mediated, as the bromide-brominium oxidation at the anode was found to help facilitate turnover of the aminoxyl mediator. This also serves as an excellent case study of how mediators can be designed and tuned to alter or enhance the reactivity. For example, this alcohol oxidation only gave 22% using tempo as a mediator. Decreasing the steric bulk around the N-oxoammonium cation in this bicyclic derivative helped enhance reactivity with secondary alcohols. There has been a lot of interest in mediated electrolysis recently, owing to the range of transformations that can be facilitated by this redox platform. The Stahl lab showed how an aminoxyl radical mediator, ABNO, can enable an alpha cyanation of secondary amines. Mechanistically, this is essentially a mediated Shono oxidation, which we discussed earlier. First, the mediator is oxidized at the anode to afford the N-oxoammonium cation, which oxidizes the amine to a reactive imine. This imine is entrapped by a cyanide anion to afford the desired product. The advantage of relying on electrolysis for this transformation is that the reactive imine is slowly and controllably formed in a current-dependent manner, thus limiting the buildup of this reactive intermediate and subsequent byproduct formation. This creative take on the Shono oxidation was applied to the late-stage functionalization of a variety of pharmaceutically relevant substrates. Another popular mediator is N-hydroxyethylamide, or NHPI for short. This mediator has recently been leveraged by the Stahl lab to achieve CH functionalization of benzylic CH bonds with a variety of nucleophiles. Mechanistically, this proceeds via first a mediated CH abstraction of the benzylic CH bond with the anodically generated NHPI aminoxyl radical. This newly generated radical is quickly captured by iodine to afford a benzyl iodide, which is subsequently displaced by a nucleophile. Here, only a small amount of iodine is needed, since after the displacement the iodide can be recycled to iodine via anodic oxidation. A variety of nucleophiles, including nitrogen heterocycles and carboxylates, could be captured using this method. Aminoxyl radicals have also been used for exhausted alcohol and aldehyde oxidation. Here, the Stahl lab found that adding an acetamin motif to their tempo mediator increased the solubility of this mediator in the aqueous reaction media needed for this reaction. Recently, AbbVie process chemists were able to translate this reaction to large-scale flow electrochemistry for the synthesis of levetiracetam. Outside of the classical mediators we talked about on the previous slides, there are many other species capable of mediating redox transfer. The Baran lab found utility in a nitrate-based mediator for an electrochemical CH fluorination. Mechanistically, this proceeded via oxidation of nitrate to its corresponding radical species, which is a potent hydrogen atom transfer reagent. This species then generates a carbon-centered radical, which is subsequently trapped by select fluoride to afford the alkyl fluoride product, as well as a nitrogen-centered radical from select fluor. This species can then go on to engage in further HAT processes in a radical chain fashion. This mechanistic hypothesis was bolstered by the observation that less than 1 Faraday per mole was often needed for full conversion. Regarding selectivity, this approach tends to functionalize the most substituted CH-bearing carbon atom owing to the stability of the resulting radical. While many of the mediators we discussed so far are commercially available, the design and synthesis of new mediators is often a synthetic chemistry challenge in and of itself. For instance, making subtle changes to quinculadine for CH functionalization chemistry requires de novo synthesis of rather complicated bicyclic architectures. The Baran lab wanted to address this limitation through the invention of N-ammonium ylide mediators. These mediators exhibit clean redox in their ylide form, are potent HAT reagents, and can be easily synthesized in a few steps with lots of opportunity for library generation. With a new mediator in hand, the Baran lab wanted to see if subtle changes to the identity of the acyl group would alter or enhance the reactivity of an electrochemical CH oxidation reaction. While the relative reactivity of this mediator was about the same as quinculadine, the site selectivity could be tuned by choice of acyl group. Although the trends are not totally clear, the site selectivity for the sclerolide oxidation could be highly skewed towards C2 over C3 by modulating the electronics of the ylide. For instance, simple quinculadine gave a C2 to C3 ratio of roughly 5:1, whereas the ortho-trifluoromethylaryl ammonium ylide gave a higher degree of selectivity with a C2 to C3 ratio of 25:1. Moving the trifluoromethyl group around the ring of this ylide dramatically reduced the selectivity for reasons that are not totally clear at the moment. Regardless, these tunable ylids showed intriguing reactivity in electrochemical CH oxidation reactions. Some mediators grant a new reactivity. For instance, different sites can be engaged when compared to classical reagents using these new mediators. A striking example could be seen in the site-selective terpene oxidation shown below. The meta-trifluoromethyl ylid gave clean oxidation as a single regioisomer, whereas quinupridine failed to give any product in the same reaction. Other mediators simply complemented existing reactivity. For example, the substrate shown here, the results are nearly identical to quinupridine for CH functionalization with respect to yield and selectivity. These mediators were also applied to late-stage CH oxidation of drug substances to generate putative metabolites for biological testing. Here, these ylids were uniquely effective for generating these material, whereas other reagents led to decomposition of the starting material. Finally, an intramolecular CH oxidation was demonstrated, which opens up the possibility of new proximity-directed CH oxidation strategies. Mediators can also be transition metals. Perhaps one of the most used tactics for mediated electrolysis is its infusion into catalysis. After all, the modulation of metal oxidation states is a fundamental aspect of many catalytic reactions. As an example, the Baran lab showed how electrochemistry can enable a mild nickel-catalyzed CN cross-coupling of aryl halides and pseudohalides with primary and secondary amines. The role of electrochemistry in this reaction is purely modulating the oxidation state of the nickel catalyst to facilitate various elementary steps of the catalytic cycle. The catalytic cycle starts with the cathodically generated low-valent nickel-1 species, which undergoes oxidative addition with the sp2 electrophile to generate a nickel-3 aryl complex. This high-valent species is reduced at the cathode to afford a nickel-2 aryl intermediate. Amine coordination followed by metal-assisted deprotonation results in an amine-coordinated nickel-2 aryl species. The barrier for reductive elimination from this nickel-2 is high. However, anodic oxidation of this species results in a high-valent nickel-3 species, which undergoes facile reductive elimination to afford the product as well as a nickel-1 species that can re-enter the catalytic cycle. This method was applied to a wide array of pharmaceutically relevant amines and arenes. These same principles can be applied to a decarboxylative carbon-carbon bond-forming cross-coupling reaction as well. The Baran lab demonstrated how electrochemistry can be integrated into cross-electrophile coupling to achieve an sp2-sp3 cross-coupling of redox-active Okada esters with aryl electrophiles. Here, the roles of electrolysis are similar to the previous CN cross-coupling example, where a reduction of a nickel-2 pre-catalyst to a reactive nickel-1 is needed. However, since both starting materials are in the electrophile oxidation state, an additional reduction of the nickel catalyst is needed to activate both starting materials. Mechanistically, this proceeds via first cathodic formation of nickel-1, which undergoes rapid oxidative addition into the sp2 electrophile, resulting in a nickel-3 intermediate. This intermediate is reduced to a nickel-2 species either by comproportionation with the nickel-1 or by simple cathodic reduction. Now in the nickel-2 oxidation state, this complex is primed for a radical capture from the carbon-centered radical generated elsewhere in the cycle. Once captured, the resultant nickel-3 species undergoes reductive elimination to afford the product, as well as a nickel-1 species that can react with the redox active ester to form a new radical and a nickel-2 complex, which re-enters the catalytic cycle. Critical to the success of this reaction is the inclusion of a silver nitrate additive, which forms a protective and functional silver nanoparticle layer on the cathode surface. If you want to learn more about this phenomenon, please check out my Research Spotlight episode from a few years back on this same platform. This reaction was demonstrated to be effective in coupling a wide range of densely functionalized arenes with alkyl cross-coupling partners derived from readily available carboxylic acids. The same reaction system was also applied to sp3-sp3 cross-electrophile coupling between two redox active esters. Here, the roles of electrolysis are similar to the previously discussed sp2-sp3 cross-coupling reaction, but with the added role of a possible radical generation from direct reduction of the redox active ester in the absence of an sp2 electrophile that can quench the reduced nickel species. Specifically, reduction of a nickel-2 precatalyst results in a low-valent nickel-1 complex, which readily mediates reduction of the redox active ester to generate a carbon-centered radical. This radical can then recombine with the reduced nickel species to afford a nickel-2 alkyl complex, which can capture another radical to afford a high-valent nickel-3 dialkyl complex. This complex undergoes reductive elimination to afford the sp3-sp3 coupled product. One limitation of this platform is the lack of specificity for the order in which the coupling partners get reduced. As such, a larger excess of one of the redox active esters is needed to favor cross-selectivity over a statistical distribution of homo and heterodimers. Again, the critical silver nitrate additive and subsequent nanoparticle functionalization of the electrode was critical to the broad scope and generality of this reaction. The reaction tolerated a wide range of alkyl cross-grouping partners and was even used several times to enable fundamentally new retrosynthetic disconnections of complex molecules. Importantly, the synthetic strategy enabled by the electrocatalytic doubly decarboxylative cross-coupling resulted in a substantial step count reduction for the synthesis of several natural products compared to the established state-of-the-art. At this point, we have sort of covered everything I wanted to with respect to how folks leverage electrochemistry in modern synthesis. However, I think it's worth a minute or two to compare and contrast this form of redox with another very popular and equally impactful redox platform, that of metallophase redox and more broadly photochemistry. So let's use tertiary decarboxylative cross-coupling as a case study for this comparison. The photochemical version of this transformation, building off the principles established by the Macmillan lab, was recently developed by some fantastic BMS scientists. Here, photochemistry was leveraged to enable catalyst reduction and substrate oxidation, resulting in a formally redox-neutral transformation. Mechanistically, this reaction first begins with excitation of the organophotocatalyst 4-CzIPN. In the excited state, this photocatalyst is a very potent single-electron oxidant and can readily oxidize the carboxylate of the acid starting material to form a carbon-centered radical and a reduced photocatalyst. The reduced form of the photocatalyst can help generate low-valent nickel-1 complex. This complex can then undergo oxidative addition with the sp2 electrophile to forge a nickel-2 aryl complex. This species is susceptible to outer sphere reductive elimination with the carbon-centered radical generated earlier in the cycle to forge the desired product, as well as a nickel-2 species that can re-enter the catalytic cycle. Critical to the success of this reaction was optimal choice of ligand. The BMS team found that nitrogen-based ligands resulted in a substantial amount of ester side products that come from carboxylate coordination to the nickel-2 aryl species, followed by reductive elimination. Beta-diketonate ligands minimize such pathways while also promoting the desired cross-coupling reaction. The reaction tolerated a wide range of arenes and tertiary acids. However, the best results were achieved with acids bearing a stabilizing alpha amino group. Unactivated tertiary acids still gave product but in lower yields, likely due to their intrinsic instability. Additionally, heteroaryl bromides were far less effective than their benzene counterparts, likely due to competitive nickel ligation. At the same time, the Baran lab realizes a reductive electrochemical approach to the exact same transformation using redox-active esters instead of free carboxylic acids, thus making the reaction net reductive relative to the starting materials. Mechanistically, this reaction is similar to other electroreductive cross-couplings we talked about earlier with a few interesting features. Just like the previous photochemical method, ligand choice proved to be important as nitrogen-based ligands, while electrochemically active, were inefficient at promoting the desired reaction. Here, a mixed ligand system of pyridine to enable the electrochemical reduction and a bidentate phosphine ligand to enable catalysis was pursued. Mechanistically, the cross-coupling is hypothesized to initiate with a pyridine-assisted reduction of the nickel pre-catalyst to nickel-1. After reduction, phosphine coordination and radical capture occurs to afford a nickel-2 alkyl complex. Next, reduction of the species to nickel-1 sets the stage for oxidative addition with the sp2 electrophile. Reductive elimination then affords the product in a low-valent nickel-1 species that can generate an alkyl radical from the redox-active ester. When bidentate nitrogen-based ligands were used, isomerization byproducts were observed. This was thought to have arisen from beta hydride elimination and reinsertion sequences. Additionally, an equally viable catalytic cycle where oxidative addition precedes radical capture is also possible. This reaction exhibited a complementary scope to the photochemical variant with the inclusion of heteroaryl halides as electrophiles. However, some of these higher-order electron-deficient heterocycles were also prone to off-cycle Minsky reactions. Overall, these two transformations are actually really similar. When you compare them side by side, you begin to see that whether a transformation is photochemically or electrochemically mediated, the exogenous redox control platforms perform the same tasks of either substrate engagement or transition metal redox state shuffling. The key differences are largely ones of setup and scope. Electrochemistry is sometimes easier to scale up with the advent of flow reactors and large-scale batch electrochemical reactors. However, electrochemistry is often challenging to scale down for small-scale experiments due to the heterogeneous features that also need to be appropriately scaled. Photochemistry, on the other hand, is very easy to scale down, and you can run a reaction on a single LED for a library enumeration. However, scale-up can be challenging due to light penetration in batch and the often long reaction times needed. Each platform has its own nuances and use cases. One way I have been thinking about these two is just that electrochemistry is heterogeneous photochemistry, and photochemistry is just homogeneous electrochemistry. They are simply two sides to the same coin, in my opinion. Recognizing this conundrum of tactical choice, a few of my friends and I put together an accounts paper highlighting many of our collaborative works between Bristol-Myers Squibb and the Baran Lab of Scripps research. At the end, we assembled a tactical guide to help the community pick the right redox platform for the right cross-coupling reaction. If you have a need for any of these types of transformations, then please give it a read. Okay, well, we have covered a lot of different flavors of electrochemistry and put them into context with modern applications. I think now is a good time to reflect and see how we grew. Before I started doing electrochemistry, I thought that it wasn't a very useful platform. It seemed like the risk of electrocution was high, and it would be a nightmare to scale. It seemed really hard to understand. After all, I remember getting a C on the exam for this subject in sophomore analytical chemistry. And above all, it just didn't seem to be all that versatile. After spending a lot of time in this field and learning how to wield it throughout my PhD, I found it to be a very fascinating and useful platform for synthesis. Throughout this talk, we have seen many examples of how electrochemistry is useful and can be used to overcome important synthetic limitations. We have seen cases where embracing electrochemistry has led to overall safer and more scalable processes as well. We have seen that the underlying principles of electrochemistry are not so complicated, as all it is simply a redox balancing act. And finally, we have seen that electrochemistry can be used and leveraged to forge a wide range of bonds across vast swaths of chemical space, thus making it a truly versatile redox platform. And with that, I want to thank Matt again for having me on, and please don't hesitate to reach out to me with any questions or comments. Thanks.
Thank you to Max for this thorough intro to electrochemistry. If you would like to learn more, please feel free to check out the resources that Max has mentioned throughout the episode. If you're looking to get some practice with your newly acquired electrochem knowledge, check out this episode's accompanying problem set. If you've enjoyed this episode and would like to support our podcast, please consider subscribing to us here on YouTube or following us on Twitter. Thanks again, and we hope to see you next time.